Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to go over how to solve a problem when they only give you the initial amounts that you start with and they give you the total pressure at equilibrium. So they're not giving you equilibrium pressures or concentrations. They're just giving you the initial pressures of the reactants, and then you have the total pressure at the end at equilibrium, and they want you to solve for Kp and Kc. So let's get into this. Okay, so in this problem we have H2 at 1.75 atmospheres and O2 at 0.75 atmospheres, and are placed in a container at 200 degrees Celsius. That is correct. A spark causes the reaction to form water or water vapor, H2O gas. At equilibrium, the total pressure is 1.90 atmospheres. And so they ask they first ask calculate the Kp. So the first thing we need to do is do an ice table because we're told it's at equilibrium and they're giving us the initial condition. So let's find the equilibrium expressions for each of the species in terms of x. So we're going to start with our equation, and we've got our ice table. So the initial conditions we have for H2, 1.75 atmospheres. For oxygen, we have 0.75 atmospheres, and we don't have any product to begin with. And then we're just going to find the change now. We know that it's going to go in this direction because we don't have any product, so it's going to shift to make product. You can't have zero of something, so it's going to shift in that direction to fill in that amount. So we're going to lose a 2x amount because we got to pay attention to the stoichiometric coefficients. So this is 2 to 1 to 2. So we're going to lose a 2x amount for the H2. We're going to lose an x amount of the O2. 2 to 1 matches 2 to 1. And then that means we're going to add or gain a 2x amount of our water vapor. And then we just add these together. So we have 1.75 minus, minus 2x. So that's going to be the equilibrium amount of H2. And then for oxygen, we have 0.75 minus x. And then for water vapor, it's just 2x. And so now at equilibrium, these are the expressions for the amounts of each of these species, H2, O2, and H2O at equilibrium. So now we have to solve for x. Well, how are we going to do that? Well, Dalton's law says that the partial pressures of all the gases that are mixed together will equal the total pressure. And they gave us the total pressure. So now we can set up the equation that the total pressure, 1.90, is equal to each of these. So 1.75 minus 2x plus 0.75 minus x plus, and then we have the 2x. So now we have this one equation. We have the one unknown x. We can solve for x. So I have a minus 2x here. I have a plus 2x. So that can cancel out. I have 1.75 and I have 0.75. So we can add those together. So 1.90 is going to be equal 1.75 plus 75 gives us 2.50. And then we have our minus x. I can add x to both sides, make it positive. So now I'm going to have 1.90 plus x is equal to 2.50. Now I can subtract 1.90 from both sides, 1.90, and that means x is going to be equal to 0.60 atmospheres. So now that I know X, I can figure out what the equilibrium or the equilibrium pressures of each of these is going to be. So, so here, oh, by the way, we should have our K expression, right? So Kp is going to be equal to the pressures of the products over the pressures of the reactants raised to their coefficient powers, right? So here, they're all gases, so we're going to include all of these in our expression. So we have one product, it has a coefficient 2, so this is going to be the partial pressure of H2O raised to the power of 2. That's on the top. And now we have our reactants. So we have H2, again, coefficient 2, so that's going to be raised to the power of 2. So on the bottom, we're going to have the partial pressure of hydrogen raised to the power of 2. And then we're going to multiply that by the partial pressure of oxygen raised to the power of 1 because there's a 1 coefficient. So we'll just put PO2. So there's our expression for the equilibrium constant. So now we have our equilibrium expressions in terms of X. We know what X is. Now we just solve for these. And so if we take this, the equilibrium, the partial pressured equilibrium for H2 is going to be equal to 1.75 minus 2x, right? Which is equal to 1.75 minus 2 times 0.6, which is going to be equal to 1.75 minus 1.2. And so that's going to give us, let's see, excuse me, 0.55. So that's going to be 0.55 atmospheres. And then we do the same thing for O2. So the partial pressure of O2 is equal to 0.75 minus X. And then again, that's going to be equal to 0.75 minus, well, X is again 0.60, so 0.60, and then subtract those, and we get 0.15 atmospheres. And then finally, the partial pressure of water vapor. So we have pH2 is equal to 2x, which is going to be 2 times 0.60. And so, again, that's going to give us 1.20 atmospheres. So we have the partial pressures now. So to find Kp, all we need to do is plug these into our expression here. So let's go ahead and do that. We have Kp is equal to the partial pressure of water, which is 1.20. So we have 1.20 squared over, then we have the partial pressure of hydrogen, which is 0.55. So we're going to put 0.55, and that's squared as well. And then we have the partial pressure of oxygen, which is 0.15. So we're going to multiply that, 0.15. And so now all we have to do is calculate and find Kp. And when we do that, we get where's my answer? 3173. So Kp is equal to 3173. But since if we're dealing with sig figs, if we want to pay attention to our sig figs, we have 3 sig figs here, we have 2 here, 2 here. So therefore, and we're multiplying and dividing, so the rule is that your answer should have the same number of sig figs as the least number, or the measurement with the least number of sig figs, which is 2. So we would round this to 32 for KP. Okay, now what about KC? Well, KC we can calculate from our equation. So the equation is KP. Let's see. I'm sorry. KC is equal to. Oh, sorry. KP is equal to KC times RT raised to the power of delta N, and delta N is the difference in the number of moles between your products and your reactants. So it's the number of moles, the total number of moles of your products in the gas phase minus the total number of moles of your reactants in the gas phase. They have to be in the gas phase. Okay, so let me erase the board and I'll be right back to do part B. Okay, welcome back. So we're going to do part B now. So part B asks us to calculate the KC value, and we can relate KP and KC by this equation here. In another video, I'll show how this is derived from from what we know from the ideal gas law. Okay, so here, since we know this relationship and we have KC, or sorry, that should be KP. Since we know KP, then we just plug everything in. Now we need the temperature in Kelvin. They gave us 200 degrees Celsius, so we're going to have to change our temperature. So temperature equals 200 degrees Celsius. We're going to have to add 273.15, and then we get 473.15 Kelvin. Okay, and then now that we have that, we can plug everything in. Now let's calculate delta N. So it's the difference between the moles of gaseous product minus the moles of gaseous reactant. So let's write our equation down again. So we have 2 moles of H2 gas plus 1 mole of O2 gas is in equilibrium with 2 moles of water vapor or water gas or steam. Steam is another name for that. Okay, so it's again, it's the total number of moles of product in the gaseous form, and we have 2 total. So we're going to take 2, and we're going to subtract the total number of moles of the reactants in the gaseous form, and both reactants are gases. So we have 2 moles here, and we have 1 mole there. 2 and 1 is 3, so we're going to subtract 3, and so that gives us a delta N of -1. Okay, so now we have our delta N, -1. We have our temperature in Kelvin, so now we just plug everything in. So we have KP. Now, don't plug in the 32 because that's a rounded answer, and if you plug in 32 you could get a rounding error. So let's go back to our original answer and use that. We will use more digits than we need for as far as sig figs go, but it'll avoid a rounding mistake. So KP is equal to 3173, so we're going to do 31.73 is equal to KC times RT, right? But we know RT, so I'm going to put this in square brackets. So R is 0.08206 liter atmospheres over Kelvin mole. Right? And so we're going to multiply that by temperature, which is 473.15 Kelvin. So the kelvins are going to cancel out. We'll put that in square brackets because all of this is raised to the power of -1. So we're going to put in -1 there, right? And then you can solve it that way as well. But let me go back to RT so I can show you some algebra that might make it easier, right? We'll come back to this again, right? So this is RT minus 1. Well, that -1 means that this is in the denominator, right? So we can bring anything that we have a power to, we could always bring it to the denominator from the numerator to the denominator, and we can just change the sign of our power here. So here's a negative, so when we bring it down, that'll be a positive. So that means that this is equal to KC. Oops, let me put that up higher. This is going to be equal to KC over RT. And so now the power is a +1. We don't need to write that. So this is equal to this, right? So then now, if we multiply both sides by RT, right, that'll cancel out. And then we multiply this by RT, right? So now, this is equal to this. So now, KC over here is equal to 31.73, which is your KP multiplied by RT. So now we can plug in RT like I did before. So then we have 3173 multiplied by 0.08206 multiplied by 473.15 equals KC. And then we just calculate this, and when we do that, we get 1242. So KC is equal to 1242.45. And again, we can round this to the proper number of sig figs, right? So here, the proper number of sig figs would again be 2, because remember, this only has 2 sig figs in it. We kept 4 because we wanted to avoid a rounding mistake. So this is 2 actually. So this number would have 2 sig figs. That has 4. This has 5. But technically, it would probably only have 3 because this has 3 because the decimal point. So the least number is 2. So that means we're going to round it to 1, 2, and then we're going to cut that off. We got to put zeros here to replace the 4 and the 2. We don't have to do it here. So anything that's to the left of the decimal point that you are getting rid of, you need to replace with zeros. Otherwise, it's rounded way too much. So that's going to be equal to 1200, or 1.2 times 10 to the 3rd power. And there you go. And that, ladies and gentlemen, is how you deal with this sort of problem. I hope you enjoyed this video. I hope this helped you out. If it did, then please like the video. Hit that like button down there. Also, subscribe to my channel. Help me out. Hit that notification bell up there so that when I put out videos, you'll get them. Make sure you click all so you can get all the videos or all the notifications. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.